Hey everyone, and thank you for inviting us here to speak. Let me just see, I'm supposed to have a clicker. Oh, I'll just use the laptop. Okay, so this presentation is about FHE, fully homomorphic encryption, which you may wonder what does that have to do with CK, and I'll touch on that towards the end, but you'll see there is quite some similarities and synergies between the two. All right. Thank you. Okay, so first off, ZAMA is a company focusing on homomorphic encryption. We're building a homomorphic encryption library, TFE-GRS, which is available open source, Rust-based. On top of this library, we're building two solutions. One is blockchain, the other one is AI. When I say we're building blockchain, I should mention that we're not actually building our own blockchain. We're rather providing the components, as I'll dig into the details of in a bit, for people that want to build a blockchain on encrypted data. So I won't go too much into this, but we have a relatively large research department focusing on this both on the theoretical side of FHE, but also on the implementation side. We're building or implementing towards CPUs, GPUs, have a small FPGA and ASICs teams as well. I don't think we need to say much here, but the motivation behind this is that data on the blockchain is inherently public, and that creates some issues. But if we can encrypt this data, then we can get around some of these things. Theft could be one thing, that people can see your data, can figure out your account balance and so on. You might not be comfortable with people seeing all this data and what they can use it for. And we also have, like MEV, some concrete issues where people take advantage of the data because it's publicly available. So what fully homomorphic encryption can do intuitively is that you can encrypt data, and then you can have someone else compute on this data while it remains encrypted. So without being able to decrypt the data, you can still manipulate the ciphertext in such a way that it makes a meaningful computation, which then can be sent back to someone who has the decryption key who can then decrypt the results. So you can kind of outsource the computation, but in a secure way where you're guaranteeing the confidentiality of the data. So for instance, we might have an encryption of X and encryption of Y, and then without decrypting this, without knowing the decryption key, you can still turn this into a third ciphertext, which is now an encryption of X plus Y. Likewise, you can do a homomorphic comparison between two ciphertexts. So this is not just looking at the bytes of the ciphertext, that would be meaningless, but you can do homomorphic computation on the two ciphertexts and then compute a third ciphertext, which is now whether or not X is smaller than Y. And more generally, you can apply a function to encryptions and then get the result of that function as a new encryption. Okay, so what we can do in terms of, in the context of blockchain is we can encrypt transactions, we can encrypt the state on the blockchain, we can keep the data available on-chain, so it doesn't have to be off-chain, and we can also mix this together with existing applications. So you really decide, and we'll see an example in a bit, you really decide which part of the contract you want to have encrypted and which part you want to have in plain text. So there's no, if you want to run ordinary applications on our FHE VM, you can do that. But then you can start bringing in or changing some of the data types to work on encrypted data instead. We're not doing anything to protect the computation, so everyone can see the logic that's being computed. It's only the data that's being computed on that we're protecting. We also have the implementation where it's up to the smart contract itself to decide what access control you want. So in other words, each smart contract decides which ciphertext can be decrypted and which can't, which makes you free to do whatever you want in your application. And we also make it very easy to mix data across different users and across different smart contracts. I'll get into the details, the technical details of this in a bit here. Okay, so some of the use cases we're looking at is tokenization, blind auctions, where instead of, so a blind auction today might be you first submit a commitment to your bid, and then there's a second phase where all the bids have been done, where you open all the bids and then you compute who won the auction. In our case, using fully homomorphic encryption, you can send encryptions of your bits, and then you can also compute without decrypting anything who's the winner of the auction. So the only leakage with these blind auctions is really who won the auction. If you want to, you can also keep that private in some sense. Games, we can generate randomness on-chain, so it's easy to deal directly with the encrypted data. Of course, you can't do massive games with these things. We also have performance challenges, as we'll see in a bit. But you can start to make simple games. Voting is another one. Encrypted identities, I'll touch a bit on this later. And of course, private transfer. So you can make an ERC20 token where you keep the balances encrypted, for instance. I have a quick demo of that or slide on that later. Okay, so diving into the more technical aspects of this. What we do is we are basically saying there is a single global public key, FHE key, under which all the data on the blockchain is encrypted. So here on the left, we have the blockchain. The green dots represent validators. They each have a copy of the public key, meaning they can do these homomorphic computations and so on. And then next to it, we have a KMS, a key management solution, where the secret key lies. So, and the orange dots here, which are the threshold nodes running the KMS, they don't have access to the actual secret key. They just have secret shares of the secret key. Okay, so there is a threshold assumption here that you need a certain amount of corruptions in the KMS before you can leak the secret key or take advantage of the secret key. But using these shares of the secret key, the players or the parties in the KMS can still do decryptions and threshold re-encryptions, as we'll see. Okay, but that's kind of our setup. Another point is we're not touching anything on the blockchain side of things, so you still get your proof of stake consensus and all that stuff. The only thing that our protocols are dealing with is in the KMS and how we keep the secret key secure. So a naive way of generating this secret key would be to have it generated on one single party and then secret sharing it. That would, of course, be insecure. So what we have instead is we have threshold key generation. So the orange dot here, meaning that the parties inside the KMS, they start out with nothing, and then they run a protocol between them to generate shares of the secret key as well as the public key, which can then be distributed to the validators and to users. When the user wants to input a ciphertext now to the blockchain, he can simply take this public key, take his input X, encrypt it, and send it to the blockchain. We're also saying here that it's not just the ciphertext he sends what we call a certified ciphertext, which is because the ciphertext comes along with a zero-knowledge proof of knowledge that the user knew this X. I'll get into the details of this in a bit, but it has a security requirement. But that's, yeah, so that's simply providing inputs to the blockchain. He just encrypts under the public key, generates a proof that he did the encryption correctly, and then sends this into the validators. When we want to do operations on this is a purely local operation or computation from the validator's perspective. So here they take an encryption of X, an encryption of Y. They apply these homomorphic operations, which can be done locally. So each validator is doing this, and each validator will then arrive at a new encryption of C in this case, so the comparison or the addition, multiplication, whatever you want, of X and Y. The scheme we have and the implementation we have is deterministic, so that's why we get consensus on the byte level of these ciphertext. And all of this stuff can be done locally. When we then want to do a decryption, so at some point you might want to know who won the auction, so you want to decrypt the winner of the auction. We send this ciphertext to the KMS. The KMS runs a threshold decryption protocol, meaning they all communicate. We have optimized protocols for our encryption scheme, or MPC protocols for our encryption scheme, that can then do the decryption, arriving at X in this case. Sometimes, of course, you don't want the X, or the plain text value, to be publicly known to the world. So what we do instead is we also have what we call re-encryption, threshold re-encryption, where the KMS starts out with an encryption of X, and then a new public key, so in this case a purple public key, and we'll see in a bit where this comes from. And then what we do is we take the encryption of X and we turn it into a new ciphertext, which is now an encryption under this purple public key. And again, the naive approach of doing this would be to have the KMS decrypt the ciphertext and then re-encrypt it, but that will of course be insecure, so we actually don't do that. We go directly from the encryption of X into a new encryption under this, of X under this new public key. Where this is useful is, of course, when the user wants to see his own balance, for instance. So in that case, he can generate a key pair locally, meaning he has the secret key to this key pair. He can send the public key to the blockchain, and then we do the re-encryption under this new purple public key into the encryption of X, send this to the user, and then since he knows the corresponding decryption key for this purple key, he can decrypt and obtain X. Okay, so I want to dig into how the FHE works a bit more from the technical perspective. We do primarily one modification. We add a pre-compiled smart contract to the FHE that allows us, for the most part, to call into our homomorphic library, TF-HERS. And then I also want to cover what we call honestly obtained. So since we want smart contracts to be able to decide the access control logic, so the smart contract developer really decides what could be decrypted and not be decrypted. That also means that a malicious user could submit a malicious smart contract that would just decrypt everything. So you could go on the blockchain, you would grab a ciphertext, you send it to your malicious smart contract, which will then decrypt it, and that way you can reveal all the data on the blockchain. So to avoid this, we put a limitation that smart contracts can only ask ciphertext to be decrypted that they have honestly obtained. And then forcing this notion of honestly obtained could be done using zero knowledge proofs, where you kind of prove along the way that this was actually done correctly and that you had the rights to kind of arrive at this ciphertext. But as I'll talk a bit about later, this is actually really expensive to do verifiable computation for FHE. So instead, we have more a software-based approach or logical-based approach, where we enforce that smart contracts, they only ask honestly obtained ciphertext to be decrypted. And I'll dig into how we do that in a bit. I see a counter here. Is that a timeout for the talk, by the way? Yeah, okay. All right, so I'll go a bit quick on this. So basically what we do is we have a smart contract A here on the side. They don't operate directly on ciphertext. They rather operate on handles to ciphertext. A handle is just the hash of the ciphertext, so this makes them smaller, makes them easier for the smart contract to store and pass around and so on. Then whenever the smart contract wants to do anything with this ciphertext, it sends it to our precompiled smart contract, which has an area of memory. So this is just a normal area of memory that is allocated and unreachable by the smart contract, where we keep track of these handles and how they link to the ciphertext, and also we have an access control list. So in this case, we say that this handle HX was honestly obtained by a smart contract A if A is in the list LX. And that's kind of our property. So when the user provides this certified ciphertext in the beginning, the sender here, the user on the left-hand side, sends the ciphertext along with the proof to the smart contract. The smart contract can't do anything with this ciphertext at this point besides passing it to the precompiled smart contract, which will verify that the proof is correct, that it was something that was sent to the smart contract. So we're linking this ciphertext to the smart contract, and also that it came from the sender. We verify the proof, assert that it's valid, and then we simply update the protected memory saying, okay, this handle is now pointing to this ciphertext, and A has honestly obtained this ciphertext, giving it back to A for further processing. So we now, smart contract A at the bottom has this handle to the ciphertext that it can use for processing. If we then want to do a decryption, or the smart contract wants to do a decryption, we basically look up the handle in memory. We assert that A has the permission, was in the list. If so, then we send the ciphertext to the KMS. We wait for a response. We get back the plaintext value. We now store the correlation between the handle and the plaintext, because validators can call the KMS, and the KMS will wait until a certain fraction of the validators have said, okay, this is what we want to decrypt. But full nodes trying to catch up, for instance, they won't be able to do this, so we store this correlation between the handle and the plaintext for them to see in the future, and then we send X back to the smart contract. Here is just how we call operations, same story. We see that we're using our library. We fetch the ciphertext in the protected memory, then we give them to the library, and then we mark the ciphertext afterwards as being honestly obtained. We also track if one smart contract is sending a ciphertext to another smart contract, then we update these permissions along the way, saying honestly obtained is also, or in this case, smart contract B also honestly obtained a ciphertext if it was given to it by A that had it honestly obtained. And likewise, if it returned something to A, then A also honestly obtained this ciphertext. So this way of tracking what was honestly obtained is where we can block decryption, right? The components we have the FHE VM, so this is our EVM for running these contracts, the threshold protocols for the KMS. We have a Solidity library that doesn't touch anything on the developer side, so you can use your normal developer tools to express smart contracts, and then you need the FHE VM to run them afterwards. One of the things we do is we introduce this EUINT32 data type, or other data types as well, that represents these handles to ciphertext, and we then add operations to them. You can do add, subtraction, comparisons, and so on. So I'm going a bit fast here. This is where we convert them. So you get the raw ciphertext bytes, then you convert them into a handle. So this is where we do the proof checking. We can do decryption, as I said. One thing is that whenever you do a decryption, even if you're just decrypting a Boolean value, so here you can do a homomorphic comparison between the amount and the balance you have, which gives you an encrypted Boolean. If you then want to use this in a require, you have to decrypt it first, otherwise it's meaningless. Of course, this leaks something. It's not clear what it is. That depends on the application. If you don't want to do this, we also have the CMOX operation, which is a purely local operation that doesn't decrypt anything. There are some caveats to that, but in the interest of time, I'll skip. And we can do the re-encryption as talked about. Okay, so finally getting to the point. FHE, OR, and CK, the way we see it is that these two things, they really come together. So both of them are kind of like a privacy solution for it. One benefit of FHE is that it gives you this composability, especially when data is coming from different users. That's kind of hard to do in CK. And also with FHE, we can keep everything on-chain. Oh, okay, the counter went up again. Okay, so to dig into this a bit, if we were... Okay, okay. So if you want to do a computation, so say you store commitments on-chain using CK. When you want to do a computation on this, you need to do that computation on the plain text data. So in this case, we have, the validators will have 2 commitments on-chain, and then the user would have the corresponding plain text data. When he wants to do a computation on this, he can do the computation at the bottom. He computes Z, which is a function of X and Y, make a new commitment to this and a proof that he did the computation correctly, push this to the chain. This works nicely if there's just a single player doing this. The problem is, what if you have 2 users and they now want to mix this data? Then the question is, who actually does this computation? Because the computation needs to happen on plain text data. With FHE, and since everything was encrypted under the same key, this was trivial to do, right? But this is one of the big differences between FHE and CK. Another thing is that CK is typically used, for instance, in an identity solution to prove that certain statements are true. The way we see it is that you can do the same in FHE, but instead of proving and then checking the statement, you basically compute the statement homomorphically, and then you can check that it was true afterwards. So if you want to attest that someone has a certain age and so on, you can just compute whether or not this age is above a certain limit, and then make a requirement on that. So you can also build some of the same applications with FHE. Okay, I'll stop here. All right. Thank you.